Eric Archer here from TI, and today we have the Hip Hop M.D. who's going to walk us through light on Earth in today's Smart Space video lesson. Hip Hop M.D., tell us all about light on Earth.
Hey, how's it going, Eric? We are talking about lights on Earth, which is amazing, right? We all see the sun. We have lights inside our house. We turn on when it's dark. But a lot of times you just do these actions and we don't really think about exactly what's going on. What is it about light that actually makes it light up, you know? So we're gonna get a little lit on this topic and talk about exactly what is light on Earth. And there's so many fun elements to be able to kind of dive in. But I'm gonna start off with this fun fact, and I got a little question for you, Eric. Do you like sunsets?
Love them. Love sunsets. They're a lot of fun to watch.
Yes, they're so much fun to watch. Sometimes it might be a romantic sunset with your loved one. Sometimes you might just go out and you just want to get a breath of fresh air and just kind of wind down from the long day. And so you go outside and you're watching the sunset. So a little thing that you guys may not know, a lot of us love sunsets. We've seen sunsets and there's so many different colors happening in the sky. But did you know that when you watch the sunset, you're not actually necessarily watching the actual sun set? Let's break this down a little bit, right? So we have the sun in the sky, and obviously over time it starts to get late, depending on where you're at in the world. 8 o'clock, maybe right now, which on the West Coast is around sunset time. The sun now comes down over the horizon. But the light that you're seeing is actually the light from a sun that is already set. So when you're seeing a sunset, the sun is already set before your eyes are even seeing it. And that's because of something that we call refraction, which is what I'm going to get into here a little bit. It's a little trickery that the sun does, right? So obviously the Earth is round, spherical. So as the sun is coming down the horizon, light what we call bends, right? We talked about the atmosphere and how there are so many different particles and different things inside the atmosphere. It's not clear, right? The air isn't clear. We think it's clear, but there are different things like nitrogen, oxygen, molecules. If you're in an area where it's bad air quality, like LA, right? You have air pollution. You have all these different things that now the light has to be able to navigate and bounce off all of these particles. So the light does something that we call refract. So I have a cup of water here. And we see through this cup of water, you can see me behind here, and I have a little knife. We're gonna dip this inside here. When we dip this inside, boom, and hopefully you guys can see that a little bit there. But in a way, it kind of almost magnifies what we see as this knife, once it goes into the water, it now seems to bend and go at a different angle. It seems a little bit larger, right, than the actual knife itself. It's not because the knife is getting larger as it goes inside the water. This is something that's called refraction. Because now as light is bouncing through these different H2O molecules here in our water, right? That's hydrogen, 2 oxygen molecules right here. This now is what we call refracting because the light is bouncing off these molecules and it's actually changing what we see as this knife underneath the water. And that's something that we call refraction. And the sun does that as well too. When the sun is setting, all these molecules, right, are bouncing off, all these light particles are bouncing off these molecules in the air. And so that light is actually bending and refracting. So by the time the sun is already set, that light is actually bouncing and reflecting off these molecules and coming into our eyes, which is what we perceive as light. So next time you're out on a little sunset watch, Eric, just remember the sun already set before you actually saw it, which I think is pretty cool.
That is cool. That's really neat. I like that demo with the knife, the little knife in the water too. That's kind of trippy.
Yes, it is, right? Because you see it, and we've all kind of seen demonstrations of that. You can use that with your finger. You can put other objects in there, but all that light is doing is now bouncing off the particles inside the water there. And so that's what we see as refraction. So we're going to dive into a little bit other elements here, which I think are really cool in order for us to really truly understand light on Earth. So I'm going to pull up this slideshow here, and we're going to break down a little bit about light on Earth, all right, for you guys to understand a little bit more. So we talked about the sun, right? The sun provides us with our source of light. In the daytime, that's how we see things, right? Because we have this large glowing plasma mass that's inside our solar system that's giving us light. And we talked earlier about photosynthesis and how plants need that light to convert that into energy. So light from the sun is very important. And the atmosphere, as we talked about, we saw in our example where the knife actually looked bigger, is because of all these different light particles that are being reflected and refracted within the water. And that's caused by our atmosphere, right? This atmosphere that we have that protects us, right? We talked about radiation, solar radiation, how our atmosphere protects us. All these different particles within our atmosphere not only protect us, but they bounce off this light that we see from the sun. So light gives off some of the electromagnetic radiations broken down across what we call an electromagnetic spectrum, which we'll dive into a little bit later on. But it's good to know that there's a spectrum of light. What we see as this orange mass of light, there are other forms of light that exist all around it. So this looks very complex, but I just want you guys to see a visual of this, and then I'm going to break it down a little bit more. Light does something that is very, very unique, what you call the wave-particle duality. It has the ability to act as a wave, and it also has the ability to act as a particle. It can do two things at the same time. And we know this because of a test that was done way back by Thomas Young, which proved this duality. So we're going to actually talk about that, right? Because it seems pretty complex. Light acts as a wave and a particle. Like, what exactly does that mean, right? So we know waves, right? We know waves with our sound waves, and we've seen all pictures of waves with frequencies and troughs, and they kind of bounce up and down. We have different waves and we have different wavelengths. So light can act as a wave moving through the air. It can also act as a particle, little objects, right, that bounce off different things. So we call photons, right, and have certain mass that bounce off different things. So that test that we saw is actually pretty simple when you think about it, when you break it down. So I have a little cardboard box here with some cutouts, okay? And I'm gonna hopefully see if we can actually be able to visibly kind of see this. This is not exactly how the test was performed, but this will kind of give you a good visual of exactly what was taking place. So I'm gonna pull up my phone here, which has a nice light on my phone, okay? I got my flashlight, boom, right here on my phone, which is a form of light, right, by the way. So I have this cardboard cutout, and this cardboard cutout is special because I've hooked some holes inside it here. So we have some holes that we can see through. And in this test, in order to find out what exactly light is, he did this test where he had a flashlight, not necessarily a flashlight like I have, but very similar, okay? And he held this box right here, which had different cutouts, right? And he did something where he shone a light through that, okay? And you may not see this here. You can kind of see a little bit in the background, that light's now going through the holes, and you see the holes on the opposite side, which is something that we've all kind of familiar with, right? We know that if we shine light through a box or through an object or holding up a flashlight, it's going to come out into the shape of what we see. So you see those holes, and we see the slits now being projected on the other side. But in this experiment, he found something that was very, very unique. Light, obviously, we talked about, is a wave, right? So as that light now from the flashlight is bouncing through here, it's a wave, and those waves go through these holes and project on the other side. But in this test, he found something very unique. Not only does it act as a wave and go through here, he realized that each different individual hole now possesses different particles from that light. So he was thinking that he was going to see the same wavelength on the opposite side, but what he found out was there were different particles that were now shown because there was a spectrum. When this light now bounces through here, it doesn't look the same as when it started in here. It now spreads across whatever film or whatever background you're going to have through here. And so that's how he was able to determine that light behaves in multiple different ways. I always like to say, you know, I'm a big hip hop fan, and I love Drake, right? Drake can sing and he can rap, right? But light is something like Drake, right? He can sing and he can rap, or he can do them at the same time. So we have this light right here. Not only is it acting as a wave at certain times, but at certain times it can also act as a particle and shoot photons and bounce off different things. And that's one of the things that's just fascinated scientists, fascinates me to this day, the fact that it can do two things simultaneously, or it can do them at different times, which is something very, very cool to remember about light. That's pretty awesome. So I always kind of love to kind of show that breakdown of exactly how light works across that spectrum. So
Well,
now
Hip Hop MD,
yes,
sorry to interrupt you.
Ask away.
I think you're the first person that's ever described Drake as light particles and waves. So well done. I think that's awesome. I love that analogy, and it's so fitting. So very good.
Yes, absolutely. And it's important to know because a lot of times we think things have to be mutually exclusive, like it could be one or the other. But you always remember light, the fact that it could be a wave and it could be a particle, and could do those simultaneously, seamlessly at the same time. And we'll really see exactly how that works when we go over what we call the electromagnetic spectrum, which showcases different wavelengths. And that's going to give us a little bit better understanding. So next time you're listening to a Drake song, remember light can be like Drake and act simultaneously or individually at the same time. So that's really, really cool to know. So I'm going to go back into presentation here, okay? And we are going to talk about the electromagnetic spectrum. So spectrum is something that has different elements across this now longevity of what we call light, okay? So it ranges all types of electromagnetic radiation, light, visible, like lots of different elements. So we're going to kind of dissect all of these individually. So everything from visible light, the light that we see, to light that's used on medical equipment, X-rays, right, is a form of light. And these are expressed in different ways. We have energy, we have wavelength, we have frequencies. And you can see here from this chart, from the beginning of the electromagnetic spectrum, we have these waves that are very, very long. They're spread apart. But as you go over that spectrum and you eventually come into the visible light, now these wavelengths now become much, much, much smaller. And we're going to talk about a little bit about why that actually works. So this is the electromagnetic spectrum, and this is really, really cool to know. We're going to do a kind of brief overview and then kind of dissect a little bit more into this element. But this is a spectrum, and we know different elements of light. We've heard about radio waves, right? Next time you're listening to your favorite song on the radio, that's a wave, right? And in a way, that's a form of light because it's actually a wave. So that goes across the electromagnetic spectrum. Microwaves, which power our common electrics, so electronic items. So your phone, the communications on your phone use microwaves. We have infrared waves, which are invisible, but they're things that we call like thermal. So sometimes if you've seen night vision goggles, or if you've seen like pictures of snakes or amphibians or certain other reptiles, they use our infrared waves to be able to identify their prey. And that's all by heat. They can actually see visible wavelengths right there that enable them to be able to see infrared waves. And we can't see that as humans because it's too short on the wavelength. The only wavelength that we're able to see is what we call the visible light. So that's the white light that we see from lights in our rooms. That's the visible light that you see from rainbows in the sky, the different colors that we see. And then we go to ultraviolet rays, which are from the sun. It gives you sunburns and things like black lights. If you ever use black lights in your house, that's UV rays. And then we have X-rays. If you ever gone to the dentist to be able to get your teeth looked at or broken a bone, those are X-rays, which are a form of light on the electromagnetic spectrum. And then all the way to gamma rays, which now Incredible Hulk, right? He was flooded with gamma rays, and that's how he became the Incredible Hulk, because he had all these different things that are happening in the nucleus, right? So those are very, very important to know. But I'm gonna dive into a couple of different examples here to be able to kind of showcase different things on the spectrum. So we've all seen rainbows, right? You love a beautiful rainbow, don't you, Eric? Rainbows are amazing. So we've all gone and seen rainbows outside. And have you ever seen a double rainbow before, Eric?
Only once. Yeah, it was pretty cool. I thought it was my eyesight that was going bad, but no, it wasn't. It's actually two rainbows because the person I was with saw them too. So
Yes, yes. The crazy thing about rainbows is no two people actually see the same rainbow. So you and whoever you're with that are seeing the same rainbow, since you guys are at different angles, and we talked about what we call refraction and reflection, you guys are seeing the same activity happening, but you guys are seeing it from different angles, which makes it actually different rainbows. So you're actually seeing that light bouncing off and reflecting from different perspectives. So every rainbow is unique to whoever is watching it because you're seeing it in different positions. And so we have different colors, right? And we have this, right, which is the color blue, right? And this is blue, not because this is actually blue light, right? What happens with light is that different things get absorbed, right? And so all these different colors, red, yellow, all these different colors absorbed, but the only color that isn't absorbed in this object is blue. And that's what enables us to actually see colors. So the things that we perceive of as maybe being blue like this or orange like this is because the other colors within that spectrum have now been removed. And so I think in order to really understand a little bit about rainbows and how those lights work, I'm gonna see if I could do a little test right here. So I'm gonna put this sheet of paper up here and hopefully this will stay in place. Boom. Okay, you guys can see that paper right there, right? So
yes, we can see it.
We talked about before refraction when we used our knife and we put it into the water. So I have a water bottle here, which is filled with water, okay? And I'm gonna see if I could create a rainbow. You guys think I could create a rainbow? I'm gonna see if I could do this, okay? So you guys are doing this with me for the first time. I haven't done this. So we got our light back from here, and I'm gonna turn off a light on this side here so we could kind of create a little bit of darkness on this side here. We're gonna see if we could create what we see as a rainbow. So let's see if we can actually make this happen. Boom. Can you guys see that right there? If I go a little closer, a little farther away, boom, I'm gonna shine this a little bit at a better angle. But I don't know if it's visible on there, but you can see kind of in the middle of the paper, there's a horizontal line that's kind of at an arc. Can you guys see that arc? Can you see that, Eric?
Yeah, I can see the arc. Yep, keep going.
You can see that arc right there. And it's very faint. It's a little difficult to see on camera, but as long as you guys can see that little arc that's in the middle there, that is what we call as a rainbow. So we've seen that in the sky, right? When that rainbow is projected in the sky and it's broken down to an arc. The reason it's shown as an arc is because of what we call refraction. That light is bending, right? As those molecules and those particles, which are inside the water now, the light is bouncing off all those molecules and those particles, and it's creating what we see as a rainbow. If I go a little closer here, you can see it a little bit more. If I go back here, you can kind of adjust it a little bit. Next time you guys do this, try to do it in a completely dark room and you'll be able to see it. But as long as you can see that arc, which is right there in the middle of that paper, that is what we call the rainbow. And that has a color spectrum of what we call Roy G. Biv, which is very, very important for you guys to remember. Have you heard of Roy G. Biv before, Eric?
Oh yeah,
Yeah.
Roy G. Biv. Yeah, you want to tell me what that means?
That gives us the color spectrum. So the colors that we know, Roy R, which is red, and then O, which is orange, and then Y, which would be yellow. And then we have the G, which is green, and then the Biv part, which is blue, and then the color we know of as indigo and violet. Those are the color spectrums that we see. And so what happens is all those different colors, right, they move at different wavelengths. So we talked about wavelengths kind of going up and down. Each different color, red, orange, yellow, green, blue, indigo, and violet, they all have different wavelengths. Some are short, some are long, right? So what happens is this white light that we see is white isn't necessarily white. It's filled with all these different colors on the electromagnetic spectrum. It's filled with all these different colors in Roy G. Biv. But when it now goes through an object, such as molecules or our atmosphere, right? That is what now projects this different color variants that we see, that we know of as rainbows. Those molecules now, from the light, those light particles, they bounce off each individual molecule. And since they move at different speeds and at different wavelengths, they get spread out. And that's what we call dispersion. All those molecules spread out, all those particles spread out, and that creates a rainbow of different colors that we see. So that's why we see different layers on that rainbow of the red, orange, yellow, green, blue, indigo, and violet. And that's how we get all those different lights that are projected now onto an object. So that's really, really important to know and really cool to know when you're actually going out and you're seeing a rainbow. It's not just, oh, this is a colorful thing. Things happen, right? Chemistry-wise, that happen in the air, light bouncing off particles, bouncing off molecules, and those wavelengths being separated into this whole spectrum that gives us a rainbow. So next time you're out in a rainy day or post-rainy day and the sun is shining and you're looking out for a rainbow, you now know exactly Roy G. Biv, what is happening. You now know exactly why our atmosphere looks the way it does. And we know now why sunset can sometimes be a beautiful orange, a beautiful yellow, or even have purplish haze to it, all because of all those different lights moving through this electromagnetic spectrum, which is really, really, really cool to know.
Yeah, that's really cool. Light is a fascinating kind of thing. It's one of those things you can't really see it, but you do see it because it illuminates everything. But you know,
Yeah.
you see a flashlight turned on and you get a big light beam, and so it's just it's a weird kind of mysterious sort of thing. And then you throw in the electromagnetic spectrum, which visible light is just one part of. There's a whole bunch of other stuff like you mentioned earlier, X-rays and gamma rays and all kinds of other things, infrared and ultraviolet. It's hard to conceptualize those things. So I really appreciate the examples you gave today in this video and helping to illustrate those things for kids and adults.
Yes.
So good, good job. And once again, I'll give you a big hat tip for the comparison to Drake. Nice job on that.
You'll never listen to a Drake song the same ever again.
That's right. Great job. Thank you very much, Hip Hop MD.
Thank you so much. I appreciate that.